Welcome back everyone to section number 4. Again, we're talking about the net change theorem in this video. So we're going to use, the net change theorem to continue calculating out definite integrals. And then we're going to, maybe given like a velocity function and maybe a specific time interval, we're going to find maybe total distance traveled or displacement or things like this. So kind of some real world problems. And actually this is the section right here that we more formalize what was brought up kind of in our intro video. So if I go ahead and I kind of zoom back to the very first stuff that we did, and there we are, so here's the motivational stuff. We said that the area under the curve actually has something to do with the amount, the overall total that something's changing, the net change. So we called it total change because we didn't have great vocabulary in those days. Now we know maybe stuff about net area, and so net change actually makes a little bit more sense. But so if you have a function that specifies a rate of change, maybe how much water is being pumped in liters per minute, or how fast something's moving, in maybe meters per second, or something like this, then the area under the curve, aka the definite integral, this has something to do with the total change. Or more accurately, if you have, if it's below the x-axis or something like this, it's really net change. And hence the name, the net change theorem. All right, so let's go back to our stuff really quick. All right, and so yes, our first theorem and really our main theorem for this section is this net change theorem, which says if you want the net change of a quantity, say f of x, then if you add up its instantaneous rate of change, so its derivative, small f of x, if you add that all up, like the area underneath, maybe with a definite integral or something like this, then you would get the net change. And so what is, this net change? Well, it's wherever you end, so maybe like an f of b, so that's maybe the quantity that you have at the end of the interval when x is equal to b, and then you subtract away how much you had when you started. So maybe like f of a. That's the function's value where you started when x was equal to a. And so we can see, this is really not a new theorem. This is the fundamental theorem of calculus part 2, but we're using it to calculate out kind of some real world problems, We're going to be using net change here and instantaneous rate of change, So the terminology, the problems, how they're posed to us are going to look a little bit different. Another way that we often rewrite this is that we go ahead and we move this f of a kind of to the other side. And so then we would get kind of our final quantity, f of b, would be equal to f of a plus the definite integral from a to b of f prime of x dx, It's instantaneous rate of change. So again, it's where you started, how much did you change, that gives you how much you end with. Again, where you started, how much did you change, add those together, that gives you how much you ended with. Again, this isn't really surprising so much. All right, so in this class, we are focused on, good old physics applications here. So if S of t represents, the position of some moving object, and maybe we have its velocity, v of t, then the net change theorem says that we can compute the net displacement, how much, where did you start versus where did you end? Again, really displacement, a good physics term there, of an object from t equals a to t equals b by integrating velocity. That is, if you integrate the instantaneous rate of change of the position, aka s prime of t, well, that's the same thing as velocity, We went over that a lot in maybe section number 7 of chapter 2, This is going to be equal to where do you end, so your position at your ending time, b, minus your position at your starting time, when t equals a. Okay, so that's not so bad. Let's see an example, of how we actually use something like this. So an object moves along a line with velocity 8t minus t squared inches per second. Now at time t equals 0, the object is 5 inches to the right of the origin. What is the position of the object at time t equals 6 seconds? All right, so let's rewrite this problem. First of all, we notice maybe a first important part is the velocity statement, that v of t is equal to 8t minus t squared. We have this information at t equals 0, the object is 5 inches to the right of the origin, This is trying to tell me something about its original position, right? So this is an S value because S is position. So at time 0, or sometimes this is said initially, so at time 0, it's 5 units to the right of the origin. Usually to the right, we associate these with positive numbers, and to the left of the origin, we would associate those with negative numbers. So I'm going to go ahead and say positive 5 here. So S of 0 is equal to positive 5. And our goal, right, what is the position of the object at time t equals 6 seconds? So I would like to know what is the position, right, S, at time 6. So S of 6. And if I can solve this, then I win the game. Okay, so we're going to use exactly what we have up here. So I'm going to go ahead and integrate velocity, 8t minus t squared dt. And this should be equal to my ending point, S of 6, minus my starting point, S of 0. Now, right, I forgot to write my limits of integration. What should those be? Well, it should be the same a and b that we have here. So we should start at 0 and we should end at 6. Remember, this is telling me how much did I move. So start at 0, end at 6. All right, so calculating out this definite integral here, we have, let's see, the antiderivative of 8t is going to be something like 4t squared. We can check, take the derivative. Do you get back where you started? Yeah. Minus 1/3 t cubed. And again, we evaluate from 0 to 6. On the right-hand side, right, S of 6, that's the thing that I'm trying to solve for. That's what I'm hoping to find. S of 0, that's 5. Right, according to the statement up here. So now let's go ahead and plug in 6 and plug in 0. So let's see, if I plug in 6, we have 4 times 6 squared, or 4 times 36, which is 144. Minus, 6 cubed. All right, so let's go ahead and do 1/3. I'm going to do 6 times 6 times 6. So that's going to be, let's see, 2 times, and I'm going to group these, that's going to be 36. So altogether, I think I get 72. Okay, that wasn't so bad, actually. So minus 72. And again, I'm trying to solve for S of 6, so maybe let's go ahead and add this 5 onto the other side here. And so I get S of 6 is equal to 144 minus 72, so that's just going to be 72, plus 5. So that's going to be S of 6. Simplify one more time, and I get 77. Let's see if we can actually attribute any units to this thing. Right, so this originally it was 5 inches to the right of the origin. So I'm going to say that it's 77 inches to the right of the origin. So again, 77 inches to the right of the origin. And that would be my final answer. Notice, right, that at a certain point we went ahead and we added over, right, this 5 value in order to get our final position. Right? We went ahead and added over that 5 value. That's exactly what the second part is saying right here. Right? We wanted to know where do we end. And then we went ahead and we added over that 5 value here, and that was our initial position. And then we added how much did we move. Right? So this right here is again telling us how much did we move, or what was our net change in position. All right, that's all for this video. Again, this is really the heart of it. We'll see some more examples and stuff like this, certainly in your homework and in class and whatnot. But get started on that, and I'll see you guys next time.